In the following example, we will consider a coupled problem, and the coupled problem is a thermal mechanics coupling of this very simple 2D example. So the setup is quite simple. We're having a 2D beam with a certain height and length, and since we're considering a coupled problem, so thermal mechanics coupling, we also need to define two different sets of boundary conditions. So for each single PDE, so for the thermal PDE as well as for the mechanical PDE, we need to define correct boundary conditions. And the boundary conditions we are considering for the thermal problem are Dirichlet boundary conditions here at the top and at the bottom. So at the top, we are prescribing a temperature value of 30 degrees centigrade, and at the bottom boundary, we're considering or we're defining a Dirichlet boundary condition, so we're setting the temperature to 20 degrees centigrade. Here on the left and on the right side, we don't prescribe any boundary condition, but in the XML file we don't prescribe any boundary condition, which means in a finite element context, if we don't prescribe anything at the specific boundaries, it corresponds to homogeneous Neumann boundary conditions. And in the thermal PDE, homogeneous Neumann boundary conditions simply mean that the temperature gradient in normal direction of the surface is 0. And what is the temperature gradient in the temperature gradient in the thermal setup? Yeah, it's the heat flux density. So if we don't define any boundary conditions here at the left and at the right boundary, it corresponds to the modeling assumption that no heat is entering or leaving the domain via this right or this left boundary. So the only possibility that heat can enter or leave the computational domain, so the blue domain, is either via the top surface or via the bottom surface. And since we're considering a linear thermal partial differential equation, we can only expect a linear temperature gradient from the top to the bottom boundary. So we're having a temperature of 30 degrees here at the top and 20 degrees here at the bottom, and a linear decrease of the temperature here via the beam's height. So in the middle of the beam, for example, we will definitely have 25 degrees centigrade, since it's just a linear function over this coordinate, over the beam's height coordinate. So this is the setup of the thermal problem. And regarding the mechanical problem, we just define a boundary condition here at the left boundary, and the boundary condition we define is a so-called fixed boundary condition, which is also a Dirichlet boundary condition, and it means that every node here, or every degree of freedom here at this left surface, has 0x and 0y displacement, so it cannot move anywhere. The beam can just bend. So the only region where we can have a stress vector in normal direction of the surface is here at this left boundary. And the load for this mechanical PDE, so first of all, we're solving the thermal PDE, and from the temperature distribution in the computational domain, we can compute the load for the mechanics PDE, and the load is the so-called thermal strain that we are prescribing in the volume here. so the whole computational region. And the way this looks is the following. So let's start with investigating the mesh. It's a simple 2D mesh. So let's open the journal file. And it's a really short journal file. So we're creating a surface with width 1 and height 0.1 in the set plane. So we're only having X and Y components. And we're meshing it with a rather fine mesh. So with this 0.0125, so everything's here in SI consistent units. So this beam is 1 meter long and 10 centimeters in height, and we're meshing it with elements that are 12.5 millimeter in the cross section, and the only thing left to do is to define the region. So the surface region here, which we call S beam. This is the region where we solve the thermal and the mechanical PDE. And we also need to define the boundaries where we want to prescribe our thermal and mechanical boundary conditions. So this L top and L bottom are for the prescription of the Dirichlet temperatures, and this L fix is used for the mechanical boundary condition where we set the degrees of freedom in X and Y direction to 0. Okay, that's it. It's a rather simple mesh. So here we have our beam 2D CDB file that we're using. And now let's move right on to the XML file. So this Heat-Mech file is the simulation file we're using. And as always, here in this file formats tag or section, we are importing our mesh, our CDB file, and we're defining the material file that we're using. Then the domain section, we're just considering plane geometry, so 2D geometry, and yeah, we don't need to define any variable here, so we can actually delete these lines and import the region at which we want to solve all the PDEs, which is the S beam, so the whole beam structure. Then the first sequence step here is the thermal PDE, and as we've already encountered in the previous demonstration examples, we're solving the heat conduction equation in the static limit, so a steady state solution, and we're solving it in the only region that we have available, so in this S beam, and define the Dirichlet boundary conditions. So at the top, L top, we have temperature of 30 degrees centigrade, and at the bottom we have 20 degrees centigrade. Then what we want to store as a result is, first of all, the solution quantity itself, so the heat temperature, and also the gradient of the temperature, the heat flux density. Okay. Then let's move right on to the second sequence step, which is the mechanic PDE. And we're using the plane stress approximation of this mechanics PDE, since it's a 2D example, and this plane stress is allowed to be used. And again, we're solving it in the S beam region and define the Dirichlet boundary conditions for the L fix boundary at the left side of the beam. So what we're doing here is we're opening a tag called fix, which is basically the same as this one. Let's say displacement at name L fix and component, let's say X and value 0, as well as the Y component. So this is the same as this definition here. This fix is just a bit more, it's just a bit more convenient than defining all the displacement values and setting them to 0. So these two definitions are equivalent. Let's use the shorter one, the fix tag. So that's the directly boundary condition. And then we also need to define the second thing here, so the loads, how we want to excite our mechanical PDE. And we're doing this via, as I've already mentioned, the thermal strain. So this thermal strain, we're computing from the solution of the first sequence step. So first sequence step was the heat conduction PDE, and the quantity we are using to compute the thermal strain is the heat temperature. So this variable was the solution here of the first sequence step. And yeah, there is nothing more to define. These three lines, so the time frequency mapping, shouldn't bother you. This is just something that we need to set, and yeah, in the static simulation there is nothing to change here. If we were considering this in transient domain, transient analysis, then we would need to take care to couple the different time steps of the two PDEs correctly. But since we're having a static PDE, we can just leave this as it is. And then we're already at the store results section, and we are saving the primary solution quantity, which is the mechanical displacement. Then the derivative quantities, which is the mechanical stress and thermal strain, and also the pure mechanical strain, so the total strain, which includes automatically this thermal strain. Okay, so this is it. We're having two sequence step 1 and sequence step 2, and the coupling is accomplished or achieved just by defining the thermal strain as a load in the mechanical PDE. So that is it. We can already simulate it, but before we do that, let's have a brief look at the material file. So in this material file, we define our material, which is aluminum, and we need to define two different sets of material parameters. So one is for the mechanical problem from here to here, and the other set of parameters is regarding the heat conduction PDE. So if you recapitulate the thermal PDE, so it's a Laplace equation, and the type of material parameters that occur in this Laplace PDE, or in the thermal or heat conduction PDE, many names for the same equation, is first of all the rho, so the mass density, it's the heat capacity, and the heat conductivity. These are the parameters we need to define for the thermal PDE. And if we move on to the mechanical PDE, we again need a mass density, which is physically the same mass density as for the heat conduction problem. But since we're having quite a flexible framework, and this is the only way it is really flexible. We sometimes need to define the same parameter in the different material parameter sets. So we're having the same parameter, mass density, in the mechanical section as well as in the heat conduction section. Okay, then what else do we need? Of course, we need the elasticity tensor, and in this case, we're having an isotropic elasticity tensor, so we just need to define the elasticity modulus. This is the elasticity modulus for aluminum. For a classical steel, it would be 210 to the power of 9. And the Poisson number, which can also be, which is actually quite the same for a lot of typical materials. So 0.3 is the Poisson ratio for aluminum, steel, and iron. You can always use 0.3 for these type of materials since it does not change that much. And then regarding the coupling to the thermal PD, we also need to define the thermal expansion coefficient. Here in this case, it's 22 to the power of -6, and also a reference temperature. So the reference temperature is the temperature that the beam has before we apply any thermal load. So in this case, we're defining the reference temperature to be 25 degrees centigrade. And if we think about what I've said about the thermal problem, 30 at the top, 20 degrees centigrade at the bottom. So right in the center line of this beam, we're having 25 degrees centigrade, which is exactly the reference temperature that we are setting here. So right in the center, we don't expect any thermal expansion. So we're not expecting any thermal expansion of this center line here, which does not mean that we're not having any thermal expansion of the upper part and of the lower part, which is occurring. So the lower part has a smaller temperature than the reference temperature, so it will compress, and the upper part, so above the center line, we're having a temperature that is higher than the reference temperature, so this upper region here will expand. So all in all, we're expecting a deformation of the beam looking like this, so it will bend downwards since the top is expanding and the bottom is compressing. Okay, and yeah, we would not need to define this damping parameter. This would just be relevant for a non-static analysis type. So, for example, a harmonic or a transient simulation. Okay, this was the material file. Now let's move on to actually simulating our example. So let's execute the Heat-Mech XML file. Okay, so what we see in the console output, we're solving first of all the static heat conduction equation, and in the second sequence step we're solving the static mechanics PDE. Okay, let's visualize it in ParaView. Okay, let's uncheck the boundaries. We only want to visualize the result in the actual computational domain. And let's start with the first sequence step. So here in ParaView, it's called analysis step. So don't let this confuse you. This bar here, selection bar analysis step, corresponds to the sequence steps in the XML file. Okay, so apply, and let's visualize the so the first sequence step was the heat PDE, and the solution quantity is the heat temperature. Okay, so nothing too spectacular here. It behaves as we expected, so 30 degrees centigrade at the top, 20 degrees centigrade at the bottom, and we're having a linear temperature gradient over this height coordinate of the beam. Maybe let's also visualize this by plotting the temperature over a line. So let's go here, plot over line. Then we have such a white arrow where we can define the start point and the end point. And let's put this line, the start coordinate, at the center of the bottom boundary. So it starts at x0 and it ends 0.2 also at x0. Okay, maybe the y, yeah, the y is okay. And let's click apply. Then a window here on the right opens, and if we scroll down here, we can uncheck the results that we don't want to plot over this line. So we don't want to plot the element type, the heat flux density, element number, and node number. We're only interested in the heat temperature quantity. So this is this line here. So at the start, at arc length 0, so at the bottom end of this line, we're having 20 degrees, and at the end of the line, we're having 30 degrees centigrade. And right in the middle at 0.05, we're having the expected 25 degrees centigrade. So it's a linear temperature gradient. Everything is as we expected it to be. Okay. Then let's visualize the gradient of the temperature. So the heat flux density. Yeah, looks even more unspectacular than the temperature distribution. And the reason for that is, let's go back to the temperature distribution. Since we're only having a linear decrease over the height coordinate, so over this y coordinate, we can only expect a gradient in y direction. So a heat flux in y direction that we've already discussed in the beginning. We don't expect any gradient in x direction. So no heat flux entering or leaving here at the left or at the right boundary. So the heat flux, this is actually a vector quantity. Here we're visualizing the magnitude. So let's visualize first of all the x coordinate of the gradient. It's nearly 0. So this is just numerical rounding precision. We can say it's 0. It's order of magnitude minus 10, so nearly 0. And the y component is not 0, which is okay. And also visualize the vector glyphs, which look like this, which also makes sense since we have a higher temperature at the top than at the bottom. So heat is flowing from the top to the bottom surface. So it's actually entering the computational domain at the top and leaving at the bottom. So now let's move on to the mechanical PDE. So the input of the mechanical PDE is actually this temperature distribution. So because we need to set we set the thermal strain here, computed as a result of the first sequence step, so as a result of the temperature. And yeah, the mechanical PDE, if you think about the mechanical PDE and the thermal strain term that Professor Kaltenbacher told you about in the lecture, this is a right-hand side term, so a loading term, and we actually need to, so in this term, there is a delta T, and this delta T is made up of this temperature distribution minus the reference temperature, which was defined in the material XML file to be 25 degrees centigrade. So here we're having this temperature field minus 25 degrees centigrade, which is the delta T that we are considering in the thermal strain term. Okay, now let's go to the second sequence step, which is the mechanical PDE. So here we're having the mechanical displacement as our primal solution quantity, and also the derivative results, so the mechanical strain, mechanical stress, and the mechanical thermal strain. Now let's start with the mechanical displacement. Okay, so blue is small displacement, red is large displacement. So here we're having at this boundary where we set all degrees of freedom to 0, so no mechanical displacement, we're having 0 mechanical displacement magnitude. And don't forget, this mechanical displacement is a vector quantity. Here we are visualizing, in this color plot, we are visualizing the magnitude. And to actually, yeah, we could investigate the x and y components of this displacement, but maybe it's more intuitive to actually warp the vector, warp the beam according to the mechanical displacement. So we're clicking here on warp by vector, and then we need to adjust the scale parameter to actually see the deformation. Okay, so this is the deformation that is occurring according to the solution of the thermal PDE. So it behaves again as we expected. So we're having a higher temperature at the top than at the bottom. So we're expecting it to bend downwards, which it in fact does, which is a good thing. Now let's move on to the visualization of the mechanical stress. So actually it is not the mechanical stress, it's not a scalar value, it is a stress state, in German Spannungszustand, because the stress is actually a tensorial quantity in every location here. So if we click here on mechanical stress, it first of all visualizes the magnitude of the stress tensor. And in the plane stress formulation that we're using, we're only having, or the stress tensor only has xx, yy, and xy component. So what we're seeing here is that we're having a high absolute value of the mechanical stress tensor here at the fixed boundary, which is plausible because consider that you have, let's say, a steel beam, or we can consider it as an aluminum beam, and we are welding this aluminum beam here to some other structure that is not deforming. So this beam is fixed or rigidly welded to another structure, and we're heating up the top boundary and cooling down the bottom boundary. And right here in the edges and on this L fix boundary, it cannot expand or compress. It can, every point here is fixed in X and Y component, but it wants to expand or compress, but it can't. So that's the reason why we're having quite high stress values here at the rigid connection compared to the bulk region here of this beam. Yeah, then let's move on to the mechanical strain. And here we're seeing, first of all, a totally different picture. So this is the mechanical strain magnitude that we're visualizing. And again, strain, it's a tensorial quantity. So we're having the same tensor components than we had in the mechanical stress tensor. So let's start with interpreting the visualization of the XX component of the strain tensor. So the XX component means, look at this coordinate system here, the coordinate direction in length direction of this beam. So at the top, we're having a red color, which means a positive strain. So actually an expansion, and at the bottom we're having a blue color, and this is a negative strain. So we're having a compression here at the bottom. This is exactly what we expected from the modeling assumptions, and we can also see here this neutral line here has zero strain. This is the reason that I was emphasizing on the reference temperature in the material file, and that the center line has 25 degrees centigrade. So the in the thermal expansion section in the mat XML, we defined the reference temperature to be 25 degrees centigrade. And this beam, so the center line here has exactly 25 degrees centigrade. So this center line does not expand in X, or does not expand in X direction, or does not get longer. That's the better term to use. This center line won't expand or compress because it has already has the reference temperature. The top surface expands, bottom surface compresses, but the center line has zero elongation. Okay, so the last quantity we'll talk about is the thermal strain tensor, and this looks quite similar to the total strain tensor, because this thermal strain tensor is included in the total strain tensor. So this Mech strain is this Mech thermal strain plus the elastic strain tensor. So it has the same behavior that we were observing in the whole strain tensor. Maybe even a little bit better, since this thermal strain tensor does not have these strain artifacts here at the rigid connection. This is the thermal strain. Let's go back to the total strain. Here at the total strain, we also have the influence of the boundary condition, since this tensor also includes the elastic part of the strain tensor, which this quantity does not. Okay, this brings me to the end of this demonstration example. So the takeaway message basically is that you know how to define a thermal mechanics coupling in the XML file, that you need two sequence steps. First sequence step is the heat conduction PD, second sequence step is the mechanics PD, and that these two PDEs are coupled via, or forward coupled via this thermal strain term here that's on the right hand side of the mechanical PDE, and the connection that I've drawn regarding the reference temperature. Okay, thanks for your attention.